Hello everyone, my name is Pavel Ponomarev and I'm a master's student at ITMO University. Today I'll be talking about permissionless and asynchronous asset transfer. This is a joint work with Pyotr Kuznetsov from Telecom Paris, Yvonne Anne Pinolet from Dfinity, and Andrei Tankich from Higher School of Economics University. Let me start by presenting the roadmap for today's talk. Firstly, I'll give a brief introduction to the main topic of the paper, overview related work, and specify our final goal and point out some of the key problems we need to overcome. Then, I'll present the system model and some of the main primitives we assume being available. The third part of the talk is devoted to the formal problem statement, including the guarantees we aim to ensure. This will be followed by the overview of the resulting protocol, where I explain the main ideas and mechanisms behind its implementation. Finally, I will conclude with a brief summary of our work, possible extensions, and open questions. The main focus of this work is asset transfer systems that allow a set of participants to exchange valuable assets across their accounts. Such systems are widely known as cryptocurrencies. To be more specific, we focus on the systems where the set of participants actively involved in processing transactions varies over time. Sometimes they are called permissionless, emphasizing the fact that they assume no trusted mechanism to regulate who and when can join the system. In particular, permissionless protocols should tolerate the notorious Sybil attack, where the adversary creates an unbounded number of fake identities. The first and still the most widely used permissionless cryptocurrencies are blockchain-based, like Bitcoin and Ethereum. To make sure that honest participants agree on the order in which blocks of transactions are applied, the most prominent blockchains rely on proof of work and consensus, assuming synchronous communication. The resulting algorithms are notoriously slow and waste tremendous amounts of energy. To mitigate these problems, more recent proposals suggest to rely on the stake rather than on energy consumption. Some other techniques like proof of space and proof of space-time are also proposed. However, these solutions still resort to synchronous networks, randomization, non-trivial cryptography, or assume a trusted setup system. In recent works, it was shown that the asset transfer problem doesn't require consensus and can be solved asynchronously. Assuming that every account is operated by a dedicated user, there is no need for the users to agree on a total order in which transactions must be processed. One can build an asset transfer system on top of the reliable broadcast abstraction instead of consensus. Unfortunately, these solutions can only be applied in closed or so-called permissioned setting, as under the hood they use traditional quorum systems which lead them to make assumptions about the proportion of benign participants in the system. In a permissionless system where the Sybil attack is enabled, assuming a traditional quorum system doesn't appear plausible. Indeed, the adversary may be able to control many identities, undermining any quorum assumptions. ABC proposed a direct implementation of a cryptocurrency under the assumption that the adversary never corrupts processes holding 1/3 or more stake. However, this protocol assumes a static adversary, that means that the set of corrupted parties is chosen at the beginning of the protocol. It doesn't seem realistic in a permissionless system. In such a system, set of corrupted participants can change over time. The main goal of this work is to implement a permissionless and asynchronous asset transfer system. We aim to replace traditional quorum systems with certificates signed by participants holding a sufficient amount of assets or stake. We also aim to assume a dynamic adversary model. It should be noted that it's not an easy problem to solve. The notion of a participant holding stake at any given moment of time is not well defined in a decentralized consensus-free system where assets are dynamically exchanged and participants may not agree on the order in which transactions are executed. It's also important to mention that in a permissionless system, we can't rely on the fact that correct participants remain correct forever. For example, once a user has spent all or most of their stake, their account can be compromised as they are not interested in following their protocol anymore, or they can simply lose access to their account. Let me now proceed with the system model we consider in the paper. We assume a set pi of potentially participating processes. For the sake of simplicity, we assume that this set is finite. In practice, this assumption boils down to requiring that the rate at which processes are added is not too high. It should be noted that set pi doesn't have to be initially known by every process. We assume a dynamic adversary that can choose the processes to corrupt depending on the current execution. In contrast, a static adversary picks up the set of Byzantine processes a priori at the beginning of the execution. At any moment of time, a process can be correct or Byzantine. We also call a process forever correct if it remains correct forever. A correct process may turn Byzantine. We also assume that each pair of processes is connected via a reliable authenticated channel. Originally, forward-secure digital signature schemes were designed to resolve the key exposure problem. If the private key used in the scheme is compromised, then the adversary is capable to forge any previous or future signature. Using forward-secure signatures, it's possible for the private key to be updated arbitrarily many times, while the public key remains fixed. Also, each signature is associated with a timestamp. Private key n can sign messages with timestamps greater than or equal to n. This helps to identify messages which have been signed with the private keys that are already known to be compromised. Such schemes are usually modeled with the following three methods. The first signs a message using a specific timestamp, while the second verifies whether the message was indeed signed by a given process with the corresponding timestamp. The third one updates the current used private key and also destroys all the keys with the smaller timestamps. Let me note that keys downgrading is impossible. It's computationally infeasible to generate private key number n from the private key with number greater than n. Let me also remind you of the definition of joint similarities, as it plays a vital role in the resulting protocol. A set of elements L with a given partial order relation is called joint similarities if for any two elements A and B from the set L there exists element C in the set L called the least upper bound for A and B, what means that C is greater than or equal to A and B, and for any element D in the set L, if D is greater than or equal to A and B, then D is greater than or equal to C. The least common upper bound of A and B is usually referred to as the join of A and B. One of the most canonical examples is the set of all subsets of a given set with partial order relation set as containment. Also, one more canonical example is a set of real numbers with greater than or equal to relation. Now we continue with a formal problem statement. Let me now present the type of transactions we consider for an asset transfer system. A transaction is represented as a tuple. It contains the following data: an identifier of a process inside the system that initiates a transaction. We usually refer to it as an owner of transaction. Transfer function that specifies the amount of funds received by every process from this transaction. A finite set D of transactions that this transaction depends on, meaning that transaction spends the funds owner received through the transactions in set D. We refer to such a set as the dependency set. For convenience, we also define a value function that calculates the amount of assets redistributed by a given transaction. Transactions defined this way naturally form a directed graph, where each transaction is a node and edges represent dependencies. We always have one special initial transaction that is considered to be the root of the graph and that specifies the amount of the assets in the system. Such definition makes it clear how to determine the conflicts between transactions. Transactions A and B conflict if they have the same owner and intersection of their dependency sets is not empty. In order to restrict participants from issuing transactions with owners different from themselves, every transaction comes together with a certificate sigma. Certificate sigma can be treated as an owner's digital signature of the transaction. Also, every process can easily check who issued transaction using verify sender function. In a distributed asset transfer system, every process P holds the set of confirmed transactions TP it's aware of. This is a local copy of the shared state. Asset transfer system also exports one operation, called transfer, that performs a given transaction. Then we define the following properties that any implementation of an asset transfer system should satisfy. The first property, consistency, said that while a process is correct, its local state contains only non-conflicting transactions that have been actually issued. Moreover, for any two correct processes at time t and t prime, their local states are related by containment. The second property, monotonicity, guarantees that while the process is correct, its local state only grows. The validity property tells us that any transaction issued by a forever correct process is eventually included in its local state. Finally, the agreement property guarantees that all forever correct processes will eventually learn about every transaction confirmed in the system. Consistency and monotonicity are safety properties. They tell us that nothing bad ever happens to the system. Together, validity and agreement properties guarantee liveness in our system. Every non-conflicting transaction issued by a forever correct process is eventually confirmed. And now, let's overview Pastro protocol, a permissionless and asynchronous asset transfer implementation that we built in the paper. I'm going to start with explaining one of the key ideas we came up with in order to implement a protocol based on the proof-of-stake mechanism. As we said in the beginning, the notion of a participant holding stake at any given moment of time is not well defined in an asynchronous system. And to resolve this issue, we use the notion of configuration. Configuration is a set of transactions, and we consider only valid configurations, which means that they contain only non-conflicting transactions. We also define several important functions. Stake function, that allows us to calculate the amount of assets held by a process in a given configuration. Members function, that determines the set of participants involved in the protocol in this configuration. And a quorum function, that returns sets of participants that together own more than 2/3 of total system stake. Such notion of configuration is an extended version of the one used in the works that focus on the configuration of replicated state machines. Traditionally, they serve to determine a set of processes that maintains a shared state in a given moment of time. Here, we go beyond traditional notion and use configurations in order to define not only processes themselves, but also their weights in the system. So what's so special about configurations? It turns out that if all configurations of the system are ordered, they might act as consistent representation of stake distribution. Okay, let's have a closer look. Imagine that we have only ordered configurations. Then we can represent them as a sequence. For convenience, we can associate each configuration with a unique identifier, natural number. It can be defined as the size of a transaction set. So such a configuration sequence represents stake distribution that changes with time according to newly added transactions. During protocol execution, the configuration that process sees is constantly being updated to a great one. It might happen that the process skips one or several configurations from the sequence, and it's not a problem as we are only interested in the most up-to-date information. It's still true that the processes might have different opinions regarding current system configuration, and as a result, stake distribution. In order to define the actual stake distribution, we can choose the greatest configuration of all existing at that moment. We will only need to somehow deal with the configurations that are no longer relevant and make collecting certificates from them impossible. Getting a little ahead of ourselves, that's where we will benefit from the usage of forward secure digital signature scheme. So how do we order configurations? We might use a variation of Lattice Agreement. Lattice Agreement is an abstraction that accepts elements of a lattice as inputs and outputs their comparable joins. Unlike consensus, such an abstraction can be implemented asynchronously. Usually, implementation of Lattice Agreement satisfies the following safety properties. Output value of the process is greater than or equal to its input value. Every output value is a join of some set of input values, and all output values are comparable. In this paper, we implement a variation of Lattice Agreement that we call Adjustable Byzantine Lattice Agreement. The abstraction is parameterized by a join semilattice and function called verifyInput. This function checks whether some value can be used as an input for the ABLA object using given certificate. For example, it can verify whether the input came from a trusted source. So the pipeline for ABLA is organized as follows. An input value from the lattice along with its certificate is submitted to the object. If it doesn't satisfy the verifyInput function, the input value is ignored. Otherwise, ABLA eventually produces an output value along with its certificate. With the help of such a certificate, any process can easily check whether output was actually produced by ABLA object using public available verifying function verify_output. Our implementation, in fact, is generally inspired by the implementation of the dynamic Byzantine lattice agreement presented in the recent work on asynchronous reconfigurations. Another important building block of our protocol is transaction validation. Intuitively, you can think of this abstraction as a filter that won't allow any two conflicting transactions to pass it. For example, if process P2 submits two non-conflicting transactions to this object, then eventually both of them will pass it. However, when two conflicting transactions are submitted, there are two things that might happen. Either only one of the transactions passes the filter, or none of them. Let's have a look at its interface. Transaction validation accepts a transaction along with its digital signature. If the digital signature doesn't prove that the transaction was issued by the owner of this transaction, it's ignored. If no other conflicting transaction is ever submitted, eventually transaction validation instance outputs a set consisting of non-conflicting transactions that includes the given input transaction. It also produces a certificate that, similarly to ABLA, proves that the resulting transaction set was indeed an output of the transaction validation block, and every process can check it using verify transaction set function. The output set might contain transactions issued by other processes. It helps us to ensure that eventually any non-conflicting submitted transaction passes this filter in the resulting protocol. It's important to mention that transaction validation also guarantees that union of any produced transaction sets doesn't contain conflicting transactions as well. Finally, we combine all these ideas and building blocks in Pastro protocol, a permissionless and asynchronous asset transfer implementation. Here, I present a simplified version of our algorithm. Actual pipeline is a bit more complicated and uses some extra building blocks that allow us to optimize the algorithm. However, in general, it's still the same. So, this is what happens when a process performs a transfer operation. Firstly, a given transaction and its digital signature are submitted to the transaction validation object. In case a signature is valid and the transaction doesn't conflict with any other transaction, it's eventually included in a transaction set. This abstraction, transaction validation object, operates using the information from something that we will call current configuration. It basically means that all the operations are certified by signatures of participants that hold more than 2/3 of the total system stake in this current configuration. Processes sign their messages using private keys associated with timestamps equal to the sizes of their current configurations. Then, this set is submitted to adjustable Byzantine lattice agreement block. We parameterize ABLA abstraction here by a set of transaction sets as a lattice type with a partial order defined as inclusion. We also define the verify input function as the verify transaction set function that is exported by the transaction validation block. This is actually how we connect transaction validation and ABLA objects. So the only valid inputs for ABLA are the outputs of transaction validation. Similarly to transaction validation, ABLA operates on state distribution defined by current configuration. As a result, ABLA outputs comparable sets of transactions that, as you might remember, we call configurations, and that do not contain conflicting transactions. Then, we use output configuration to redistribute the stake and transfer the data from the old stakeholders to the new ones. Finally, the current configuration is updated, as well as the stake distribution which it determines. Let's talk a bit more about the stake redistribution phase here. Before updating the current configuration to a greater one, and hence changing the stake distribution, the processes perform the so-called state transfer procedure. They contact all the configuration C prime smaller than configuration C that might have been used and wait for a quorum of processes to respond. Processes from the quorum reply with a set of transactions they know so far, and also promise that they have updated their private keys to the ones with a timestamp equal to the size of this new configuration. Due to the quorum intersection property, in the future there won't be a quorum of processes able to send messages with a corresponding timestamp in a given configuration. This way, we ensure that even if later some of the processes turn Byzantine, they won't be able to break the protocol. This is a kind of way to invalidate old state distribution. As soon as sufficiently many processes have performed state transfer, new configuration can be installed in the system, and so state distribution changes. In fact, what we describe here is an adapted version of state transfer protocol for the case of asset transfer system from the recent work on asynchronous reconfigurations. Let me clearly mention the formal restrictions we set on the adversary in the paper. We assume that the adversary can own strictly less than 1/3 of the total system stake in any active candidate configuration. Intuitively, active candidate configuration is a set of transactions that can be accepted by a correct process, and no other correct process has accepted a greater set. It's basically something that represents the current state of the system. We don't make any assumptions on the stake distributions that were used in the past. Processes that owned the majority of the assets in the past and were considered to be correct can become Byzantine. Now let's summarize everything. In this presentation, we discussed the existing asset transfer systems, presented specification of a permissionless and asynchronous asset transfer system, and introduced key ideas and building blocks to solve main challenges behind its implementation. For detailed protocol description and its proof of correctness, I encourage you to read the paper in the proceedings of the conference and the extended version available on arXiv. In this work, we demonstrated that it's possible to combine asynchronous cryptocurrencies with proof of stake in the presence of a dynamic adversary. However, there are still plenty of open questions. Perhaps the most important direction is to study hybrid solutions which combine our approach with consensus in an efficient way in order to support general-purpose smart contracts. Further research is also needed in order to improve the efficiency of the solution and to measure how well it will behave in practice compared to consensus-based solutions. Finally, designing proper mechanisms in order to incentivize active and honest participation is a non-trivial problem. Thank you for your attention.